Hello? Yeah, okay. So today we will start with the second session and the third and the final lectures of this lecture series by Professor Blaizot. And I hand over to you.
Thank you. So yesterday we ended up with following expression for the influence functional for the propagator of a heavy quark. And this was given by the following expression: g squared times t. T is the observation time. It's the difference between the initial time and the final time, t, at which you make so an integral over momenta 1 minus exponential ik. Let me call r. R is the distance between the quark and the antiquark. It's a vector times delta of omega and k. Okay, so this is a very simple expression for the what you can consider as an effective action for the heavy quark propagation in the medium, and that involves an object here, which is a time order propagator of a field at, well, in coordinate space, the field at position q and the field at position q bar. Average over the medium, thermal average. Okay, and I made the point yesterday that this propagator with the zero means here omega equal to 0 and k. Let me move back to coordinate space. This time ordered propagator is given by the sum of the retarded propagator, omega 0 and r, plus I, another propagator, lower 0 and r. And what I want to do today is explain the physics which is hidden in this formula. Okay, so this would be the retarded propagator will contribute to the real part, and you have explicitly an explicit imaginary term here. And for further reference, I'm going to call this as a function of r minus v of r. I mean, the minus sign here are somewhat conventional, but I just want to fix it once and for all. And this object here, I call w of r. Okay, these are functions of the relative distance between the quark and the anti-quark. So now let me remind you, I mean, and I will be quick on that because that is not difficult, but these are general properties of this propagator, which you can find in the notes that I have put on the web. A general property of a propagator as a function of omega and q. This will be eventually the longitudinal gluon propagator. So if you want to think in those terms, you can. And now I'm going to rewrite this in terms of spectral function. So an integral from minus infinity to plus infinity, energy variable Q0, let me call rho delta, the spectral function associated with this propagator. It's a function of Q0 and momentum q, and divided by q0 minus omega minus I eta. So this minus I eta here is a sign of the retarded condition. Remind you that the time order propagator is a sum of the retarded propagator. So this is how it looks like. And some of you asked me yesterday about the poles and the spectral structure. So this is now explicit in this formula. And the other term is a distribution it exists only as a distribution on the real axis. This is I, rho delta, this is a spectral weight, omega and Q. And then there is a term which reflects the thermal averaging, n of omega, where n of omega is equal to the statistical factor exponential beta omega minus 1. Okay? So I'm going to transform that a little bit. See, I can write this denominator in terms of a delta function, which will contribute to the imaginary part here, and then a principal value of the integral. So let me rewrite this. So I'm not doing anything here. As a principal value of this integral from minus infinity to plus infinity, dq0 over 2 pi, the spectral weight, rho delta of q0 and q, divided by q0 minus omega. And then there is a term which I'm going to rewrite as I over 2. The I over 2 is coming from the fact that there is this denominator will contribute I pi times delta function of the energy, and the factor of 2 will remain here. And this can be written as rho delta of omega and q times 1 plus n plus 2n of omega. Okay? So this clearly exhibits now the real part and the imaginary part. And what I want to focus on is imaginary part. You see, in order to have, I am instructed, and this is because yesterday I was looking at large mass limit, and let me remind you an important formula that I used yesterday. We'll come back to it later, which is when doing the integration over time, we met the following expression, which I argue when omega t is much bigger than 1 is proportional to pi t times the delta function of omega. So this is because we are looking at long time behavior of the system, of the heavy quark dynamics, that we filter out the response of the plasma, which corresponds to omega equal to 0. Okay? We'll return to that in a slightly different form a little bit later. So in order for this imaginary part to be non-zero, there must be for this to be non-zero, it has to be non-zero. And the question that I want to address is, where is the spectral weight coming from at omega equal to 0? Now, in order to do that, I will first observe that n of omega, when omega is going to 0, you see, if omega is going to 0, beta is inverse temperature, so beta is fixed. When omega is equal to 0, I can expand this exponential. This is 1, which disappears with minus 1. And what remains is 1 over beta omega. 1 over beta omega, which is the same thing as T temperature divided by omega. Okay? So when omega goes to 0, this term n omega blows up, the 1 is negligible. So this whole expression here becomes approximately equal to I times T times rho delta of omega and Q divided by omega. Okay? So what I need to understand is whether this is why this is non-vanishing, and what are the processes, the physical processes, which are responsible for the presence of a spectral weight at omega equal to 0. And what I want to argue is what happened there is that there are collision between the heavy quark and the plasma constituent, and viewed differently, since this is a propagator of gluon, what will happen is that the gluon will couple to other particle in the medium. Let's think about the light quarks, and the imaginary part is coming from what we call cut diagrams, namely processes by which the gluon, a quark in the system, a light quark in the system, absorb a gluon and go to a different state. And now this is a calculation which is easy to do. So what I want to do for you is to explicitly calculate the imaginary part associated to this process here. So this is pi of omega and q, the self-energy of the gluon, if you wish. And this imaginary part can be calculated without much effort, because it's essentially proportional to the phase space for these processes. So I have the processes I am interested in is a process by which a gluon or a photon is absorbed by a quark with momentum p. So this is omega and q coming in, p plus q. And then I have epsilon p plus q for the quark and epsilon p on the left for the incoming quark. And I'm working in a regime which is the regime where p is much bigger than q. This is a so-called HTL approximation, but I'm not going to use the sophistication of HTL. I'll just do a calculation of the phase space for the process. So the energy has to be conserved. So there is an energy conservation delta function. Epsilon p plus q minus epsilon p has to be equal. The energy difference here has to be equal to the incoming energy, which is the energy of the gluon, which is omega. And then I have factors, because I'm looking at a scattering process. So there is a gain term and a loss term. So the gain term is, of course, one in which let's consider the process is going this way. So the photon of the gluon collide with a quark. So the quark has to be there. So there is a factor NP. And then the quark in the state P plus Q has to be absent, because this is a Pauli blocking factor, right? So there is, in calculating the phase space, there is a statistical factor NP, and 1 minus NP plus Q. The state with momentum P plus Q has to be emptied. If it is occupied, the process cannot take place. And then there is the other process, the reverse process, where P plus Q goes back to P, 1 minus NP. Okay? So it's just very simple phase space argument. Now, what is epsilon P plus Q? Epsilon P plus Q, since Q is much smaller than P, I can rewrite this as epsilon P plus d epsilon P dP times Q, right? And now d epsilon P dP, this is just the velocity of the particle with momentum P. Okay? And since the particle in the heat bath, the light particle, the light quarks are moving at the speed of light, they are massless particles, this is epsilon P plus Q times cosine theta, where cosine theta is a cosine of the angle between the direction of P and the direction of Q. Okay? You have a question? Yes.
To understand that this factor of NP times 1 minus N and this, if I start doing it from first principle, and when I do a sum over the wave function UU bar which gives in general p slash plus m and those kind of thing. That is the source of these terms if I do a first principle calculation.
You mean with Dirac
Yeah.
U fact?
Yeah.
Yes, but eventually you can forget about the Diracology here. It's just particles in a heat bath. So there is an occupation number.
Right.
So this is statistics. This is quantum statistics.
Yeah, I got that argument. I was just wondering if I do the
yes,
algebra.
Yes. You can start calculating this one loop diagram using textbook quantum field theory. What I'm doing here is a shortcut to tell you the physics which is involved.
And on the proportionality part, there will be the same q nu minus eta mu nu.
Yeah. There are these factors which don't play any role. I just want to understand. Yes, you're right. I mean, all these factors are there. I just want to understand why there is a spectral weight at omega equal to 0. Okay? You want to ask a question? Yeah.
Can we see it in this way, that in the real-time formalism, we have the propagator which has a 0 temperature propagator plus the one which has a particle creation and annihilation one, which depends on this distribution function times the delta function. So is this the contribution from the imaginary?
If you use a correct formalism, you're going to get the correct results. What I'm telling you is that what is the basic physics which explains the results? Okay, so what I'm doing here, I have a scattering process, which is this one. Okay, the gluon is not alone. There are quarks. Okay, so what is the phase space for that scattering? There's energy conservation. Okay, and then there is statistics, quantum statistics, including Pauli exclusion principle. Okay, that's all. So now let me go ahead with the calculation. So the difference here, you see the cross term NP plus Q, NP plus Q, NP disappears. This is a standard in this kind of calculation. So the imaginary part of pi, of omega and Q, is proportional to this integral over P. NP, I mean, there is a delta function, of course. No, the delta function I can simplify a little bit. Excuse me a second. Yes, so delta function minus Q cosine theta, and then there is NP minus NP plus Q, but NP minus NP plus Q, I can repeat the same thing because NP is only a function of the energy. So this is dN d epsilon P times Q dot Vp, and that's it, with a minus sign because I'm taking the difference between P and P plus Q. Okay, so this is now given by dN d epsilon P and Q dot Vp, this is Q cosine theta. Okay? So if you work out this integral, you will find that this is proportional to minus, well, the minus is not essential, omega over Q, the modulus of Q, the theta of Q minus omega, and an integral over dp, p squared, times d and p d epsilon p. And that combination here is essentially the Debye mass squared. Okay? So you see that, so this is just skip the detail of the integration here. So now if you look at the plane omega versus Q, you see that you have phase space for scattering if Q is smaller than omega. So let me draw this two line here. So this is a region of phase space where you do have a possibility of scattering. And now the imaginary part is proportional to this factor here. And this omega in the numerator here kills this one here. And what you end up with is a result which is finite, which involves a spectral function at omega equal to 0. Depending on the value of Q, you have a range of value of omega which are accessible. Is that okay? Okay. So let me give you the final result is there. Okay, but I can give you, in terms of, for those of you who are familiar with HTL calculation, I can give you the exact formula of the propagator, and you will recognize the various species. This is -1 over Q squared plus m divided squared plus I pi m divided squared times t divided by modulus of Q times Q squared plus m divided squared. So this is a real part, which is not very, I mean, this Coulomb interaction. And then there is, you recognize here, the m divided square times t divided by Q, which is exactly what I have calculated for you. So the message here, you see the omega over Q, the omega goes away, the Q, the 1 over the modulus of Q is coming from this expression here, and the T here is the temperature which is in front of this result. So what the purpose of that exercise is just to emphasize that what is going on in this system is that, and what is responsible for the spectral weight and for all the physics which is contained in the so-called imaginary potential, is the fact that there is a scattering processes going on in the plasma. The gluon is not alone. It propagates in the plasma. It can interact with quarks and anti-quarks. It can also interact with gluon. That will be the same calculation, but we will have to take care of other complication. But basically, the net result is just coming from this simple phase space argument that I have written for you.
Then, of course, in the propagator, you have the pole at md square, which is great, but the residue is still 1. Right? So that means when even in the medium, the gluons are swimming, there are no wave function renormalization. I mean, I would have expected.
No. See, I see your point. I guess this is not quite so. I guess at omega equal to 0, the Z factor that you are looking for is unity. Look, I don't remember the details, but there is a Z factor, because this obeys some rules which have to be preserved. Okay, so I may have skipped a Z factor. I mean, I was focusing on the interpretation of W.
I was
okay,
just
so
trying
maybe
to tally my basic.
No. You are right.
But won't you expect the wave function to be a little bit distorted because it's in a medium? Yeah, but in this calculation, where do you see that the wave function renormalization of the 0 temperature has been already taken into?
No. The 0 temperature contribution, the Z factor coming from renormalization has been taken care of. So this is extracted, but there could be some remnant of the I mean, the fact that the gluon is not always a gluon, sometimes it's a Q-bar pair, okay? So there is a Z factor associated to that, which I am not sure I have correctly incorporated here. But the spectral function for this gluon in the medium is very well understood, okay? Okay, so now this is, if you Fourier transform this, if you Fourier transform this object here, you get the famous function, which, I'm sorry, it's also called phi. Let me use a slightly different name of m d by r, which represents W. So W of R, which is the imaginary potential, is proportional to this function phi. And this function phi has the following structure, which I already commented in the colloquium last week. It goes to 1. In fact, it's not quite 1. I mean, it goes to 1, but the 1 represents, in fact, twice what you call the gamma, the damping factor of the heavy quark. And then what I want to emphasize is the starting point here. So this is as a function of m by times r. Okay, this is 1. And this region here is, in this region here, phi of r goes like r squared times log of r squared, or x squared, let's say x squared log x squared, where x is this quantity m by times r. So you see, you were asking me, I guess you were asking me yesterday about short distance physics, okay? The short distance, I mean, first of all, I mean, this behavior here, this is what some people call color transparency effect. Or I mean, the small, or if you wish, this is the dipole cross-section that Zoran was talking about. I mean, this is a fact that when the two color charge of the quark and the antiquark are very close together, then the gluon in the medium don't see them as individual charges. They can't resolve the charge. So the imaginary part goes to 0, okay? But there is a log which indicates that if you go to very short distances, then the calculation is sensitive to some scale. Okay, and here you see we have made an approximation in doing this calculation. We have made an approximation that this is valid only if Q is small compared to P. If the momentum exchange here is small. Okay. Now, if you go to very short distance, you have to relax this approximation. This can be done. You will find a log with a different cutoff than the Dovay mass if you do that correctly. Okay. So now we have understood what happens in the limit where the mass of the heavy quark is taken to infinity. And you see, even in that limit, there is non-trivial physics. Okay, this is the influence functional for the propagator, and it shows that the propagator is not simply, with the effective action, if you wish, the phi is not real. It contains an imaginary term. This is what nuclear physicists will call the optical potential, which shows that non-trivial physics is coming in, and that non-trivial physics is actually quite simple. It is due to collision with the constituent of the medium. So now I would like to change a little bit perspective and go beyond the infinite mass limit, and I would like to do that. Since you have a talk yesterday by Yukinao Wakamatsu, I would like to do that by using a different approach to the whole problem, which is largely equivalent in terms of physics content, but in which things will show up in a different fashion. So I will return a little bit to this in a little bit later. But I mean, unless you have question, no, I'm going to abandon for a moment the influence functional and return to the density matrix. I mean, the formalism which I'm going to use is a little bit more powerful, even if I believe that the physics comes out a little bit more explicitly in the influence functional. So I will return to the density matrix and rewrite the equation of motion for the density matrix in simple way. Okay. So I can leave up. So let me go back to what I did in lecture 1. And oops. If I have time, I will explain what happens if we relax the large M limit in the influence functional. But let me go back first to the density matrix. So the density matrix, remember, evolves in the following way. If I have some evolution from T0 to T with some generic evolution operator, the density matrix evolves with evolution operator on the left and the right. And it obeys an equation which is of the form E d by dt d of t is equal to the commutator of H with d of t. Now, H is, I can rewrite H as H0 plus H1, where H0 is the Hamiltonian of the heavy quark without the plasma, and the H plasma is, which I called HB earlier, is the Hamiltonian of the plasma without the heavy quarks. And then I can use a so-called interaction representation where I write U of t and T0 as U0 of t and T0, where U0 is the evolution operator associated with H0, and then there is the interaction operator T of T0, which is the basis of the perturbation theory. This object here is a time-ordered exponential of I times the integral from T0 to T of dt prime H1 interaction of T prime, okay? So I'm just doing standard perturbation theory at the moment. And and then I'm going to rewrite, to integrate this equation. I mean, well, first of all, I have to rewrite this equation in terms of the interaction representation. So this is completely standard. And what I get is d by dt of d, let me call it di of t, is equal to the same commutator, h1 I of t di of t. So by going to the interaction representation, I'm just I'm just eliminating the trivial evolution due to the free part of the Hamiltonian and focus on the change in the evolution, which is carried by H1. Okay? So now let me do the following thing. I can integrate this equation. di of t is equal to di of T0 plus, I should have written this with a minus I here. So it's minus I times the integral from T0 to T of H1 of T di of t prime, sorry, times dt prime. Okay? That's the equivalent statement. Okay, if I take the derivative, I recover the result. But now I'm going to do another trick. I am going to rewrite the equation d by dt of di of t I'm going to replace here di of t by this expression here, okay? So I get minus I hi1 of t. The di of t contains the di of t0, okay? And then I have another term in which I'm going to replace the di of t prime by this first term here. Okay, so I get minus I, so it's minus t0 to t dt prime. And I have hi1 of t prime. And then this di t prime, I replace by, no, actually, excuse me, I just hold on a second. Just going too fast. Child of t, that is correct. Then I have minus dt prime. Yeah, I'm sorry, I'm just replacing, I'm sorry. This is there that I should replace things. So this is here that I replace di by this expression here. So now I have the second term here, which is hi1 of t prime commutator with di of t prime. And this is integrated with t prime. Okay? In principle, if I have not made any mistake, this is just tautological. It's the same equation. I have just iterated once equation, right? This is an important trick that is going to happen now. Okay? So this equation is perfectly fine, and I am going to ignore this term here because I can always assume that yeah, let's say the basic argument is that I'm going to assume that in equilibrium, that is in the density matrix at T0, the average value of A0 is 0. So this is a sketchy argument. I mean, I don't have a better way right now to say it, but I'm going to ignore it, this first term, okay? So I have an equation now for the density matrix, which is completely equivalent to the first one. I've just iterated once. So if I would replace di of t prime here by di of t0, this would just be second order perturbation theory. But now I have a more complicated equation because this is d of t prime, which is there. So what is going on here is somewhat equivalent to what we did yesterday when, I mean, although it may not be obvious to you, but it's somewhat equivalent to what we did yesterday when we were expanding the influence functional to second order and then exponentiating the result. What we are going to do here is somewhat similar. We work out what looks like a second order perturbation theory, but because I will keep t prime, I will do something about t prime in a second, but because I keep a time argument here, I'm going beyond second order perturbation theory. In fact, I'm resumming a whole set of diagrams which are equivalent to the diagrams which were included in the influence functional yesterday. Okay? So now I can do two approximation. And these approximation are essentially those that you can now was mentioning in his talk yesterday. So there are two approximations. The first one is to assume that at time t0, the full density matrix is the product of the density matrix of the heavy quark times the density matrix of the plasma. Okay? So this is assuming that at the initial time, there is no correlation between the heavy quark and the plasma. This is not a very strong assumption because you can always consider an initial time where you start with a system in which you put heavy quarks. They don't have time to interact, so there is no time for correlation to develop. And the second approximation is that I am going to assume that this first approximation, in fact, remains valid I mean, approximation is an approximation at any time t in the right-hand side of the equation. You see, it's if there are correlations, this is certainly not true that this factorizes. However, if you go beyond that approximation, that involves necessarily some development in time. And the development in time involves the Hamiltonian H1, right? Therefore, if you assume, this is a weak coupling approximation, if you assume that H1 is some sign small, then that approximation is quite reasonable. Okay. In terms of the influence functional, in fact, this is something I have not mentioned to you, but in terms of the influence functional, this is a statement of weak coupling, which is really a statement about G times A0 being small, Okay. But now if you do that, then you can easily obtain the following result. You can do the trace over the plasma degrees of freedom, and then obtain the following from I. You can trace over the plasma degrees of freedom, and then obtain an equation for. Let me not write it for dq. You see, the trace of the plasma degrees of freedom is hard in general to perform, but if you factorize the heavy quark density matrix with the plasma density matrix, then the trace of the plasma degrees of freedom becomes quite feasible. And then if you do that, you get the following equation. It's minus g squared, the integral from t0 to t dt prime, and then there is an integral of x prime. So I'm now skipping a number of steps, x, so NA of t prime x prime, let me dqi of t prime times delta bigger t minus t prime x minus x prime plus Hermitian conjugate. I mean, there is some algebra to perform. This NA is a density of color charge. I will say more a little bit later about that. But I think if you forget about the A, it doesn't matter. So this is the equation you get for the reduced density matrix. You know, this is valid in the approximation where I assume factorization on the right-hand side of the equation of the density matrix into these two components. Of course, the final result is not a factorization form, but but on the right-hand side, I can approximate the density matrix by a factor 4. And the second approximation is a Markov, is what will lead to a Markov equation. For the same reason that I assume factorization, now I'm going to assume that in the right-hand side, I can replace diq of t prime by diq of t. The same argument, that the difference between diq of t prime and diq of t involves evolution. And that involves higher order in the interaction with the medium. Or another argument, which is more or less equivalent, is to remember that the evolution of the quark density matrix is slow compared to all other processes, in particular compared to the time scale which controls the propagator here, and therefore that is supposed to be a reasonable approximation. Now, if you do these two approximations, then you have an equation which is local, which is Markovian. That is what you still have a non-trivial integral of a t prime, but the important point is that the density matrix at time t is given by a differential equation which depends only on the density matrix at that particular time. Okay? Are you still with me? This is going fast, I recognize, because I have to skip the details in order to get somewhere. Okay. But anyway, this is well documented. And this is essentially equivalent to what, in slightly different notation to what Yukinawa was explaining yesterday. So now that I have an equation, I want to solve it. And to do that, I need to perform some manipulation, which again, I'm going to not to do into great details, but just indicate what goes on. Yeah. Oops, sorry. Yeah, I'm sorry.
So the way I see this equation is that it's like an integral transform with the kernel being the right piece of causal propagator.
Yes.
Okay. Now, if you are looking into this equation, say order g to the power 4 and things like that, will there be product of propagators and all possible combinations coming from Wick's theorem?
Well, I don't know how to answer that question. It's a bit tricky, but you see what we're doing here. Yeah, actually, yesterday I made a completely wrong statement. When discussing the exponentiation of a second order result, I was referring at some point, I guess, to the exponentiation of connected diagrams. This is complete nonsense. Forget that. Sorry about that. But what is going on here is somewhat similar. It's the fact that you see, this is somehow iterating a second order correction. Okay, if you allow me to draw a diagram, what is hidden here? You see, it's a density matrix. So let's assume a density matrix for a single quark. Okay, so I have a quark here line. So I have, you see, I have H1 acting twice. So I have, it's always going to be the same type of diagram. I have this one, and I have this type of diagram. You can, if you look at the structure of the density matrix. And now what I'm going to do is that I'm going to consider this kind of thing, roughly speaking, as a self-energy for the density matrix evolution. Okay, and what this equation does, even though it looks second order perturbation theory, it's second order perturbation theory in this class of diagrams, which are then iterated to all orders. Okay, that's a way to think about it. Okay, so it's a trick, which it was invented long ago by I think this equation is called the Redfield equation. It involves a kind of weak coupling. This is what people usually refer to Born approximation, and the other one is a Markov, so it's also known under the name of Born-Markov approximation. Okay, so it's a nice trick. I mean, it's when you made it for the first time, you are a little bit puzzled, but it is good. It is good, and what it does effectively is iterating those diagrams in very much the same way as a functional influence functional does. So it's basically the same type of physics ingredient. So now let me, perhaps in view of time, because I want to show you I want to get somewhere. And the somewhere, I would like to go all the way to the semi-classical approximation. And since I have spent time on other things already, well, let me write the equation in the form. Let me write the equation we end up with, and then I will say a few words of explanation. So, after some manipulation, which I'm not describing in detail, I can rewrite the equation as follows. It's so this is a formal statement. It says that all this object here is a linear operator acting on D, right? And what I want to do is to analyze this linear operator. And this linear operator, I'm going to write as L0 plus L1 plus L2 plus L3. There's also an L4, which I won't write explicitly. So L0 is such that L0 acting on DQ is just minus I HQ commutator is DQ. That's a standard Schrödinger equation, if you wish, or von Neumann equation for the density matrix. That's the Hamiltonian evolution of D. Then there is an L1 acting on DQ, which is minus I over 2 times the integral over coordinate x and x prime, v of x minus x prime times NA of x, NA of x prime dq. Okay. So that's a typical Coulomb interaction, if you wish. Okay, so v times n is a Coulomb interaction, commutation with dq. I mean Coulomb, I mean a correction to the Coulomb. L2 acting on dq. So this is where W comes into the game. X prime, W, x minus x prime times. So the anti-commutator NA of x, NA of x prime, anti-commutator with dq minus 2 times nxa times dq times NA x prime. And this particular structure is called Lindblad. I mean, Lindblad is the name of a physicist, but this is the equation that Yukinao was mentioning yesterday. This particular structure where you see there is density matrix, density, and then commutator of the product with the density matrix. That's this particular structure is the structure of the Lindblad equation, which has the Lindblad equation as a property to preserve the trace and the positivity of the density matrix, which the general equation doesn't have. And then there is another equation for L3, which is I over 4 times t times the integral over x prime, w of x minus x prime. And then there is another bits of physics coming in, NAX, NAX dot, commutator with DQ, plus NA DQ NXA dot X prime. Okay. And then, as I said, there are, so this term here involves the derivative of the density. And the derivative of the density is a part of the physics which leads to dissipation, right? And I will show you that, I will do the explicit calculation for the one body, for the density matrix of a single quark. And you will see that appearing here. This doesn't have the same structure as this term. And that is why when you stop your expansion here at order L3, this you can view as an expansion in terms of linear operators, then you need an extra contribution, which is called L4. And this L4 is quadratic in the velocity, so a priori it is small in this particular regime, but it is necessary in order to preserve the Lindblad structure. I mean, it is necessary. As I said yesterday, there is a trade-off. I mean, you may insist on the Lindblad structure at a cost which is not negligible. And on the other hand, because the term L4 will be proportional to the square of the velocity, which is small, you don't do a big correction and you lose the asymptotic behavior of the solution. So it's a matter of a balance. Nothing is perfect as soon as you make approximation. So I guess let me, unless you have questions, let me quit the formal part. What I want to do now for the next 5-10 minutes is to apply this to the case of a single heavy quark, and I would like to go all the way through to the derivation of the transport equation, okay, and show you how we get out of that equation, which look familiar and which have been used successfully in the phenomenology of heavy quark dynamics. So that will be there, and then I will show you a few results on slides for the last 15 minutes of the lecture. In the first, oh yes, there is, thank you. There is, the dot is acting on the prime, yes. This is, thank you for watching so carefully. Okay.
Yeah, I have a question. So
Yes.
in order to compute the n dot, you
Yes.
also need to know how the quark system talks to the bath. Because
Absolutely,
dissipated.
absolutely. The n dot is coming from the, you see, when you go to the interaction representation, you have to, I mean, remember the interaction is zero at some location of the quark coordinates, right? And the quark coordinates now is transformed into a time-dependent coordinate.
So
okay.
yeah, I mean, the way I say this is sort of a integral differential kind of equation. So do you really need those, like when you try to solve this?
Yes, I'm going to solve that in a very specific case. I need a further approximation, which is a semi-classical approximation.
So you can like tackle this kind of equations where the right-hand side, the integral can be doable in closed forms for those pieces of Hamiltonians of.
Yes, yes.
Okay.
Yes, this can be done. Yes, this can be done. This can be done. I have, I mean, it would require, I mean, it becomes a little bit technical, so it would require more time to do that on the board, but this can be done and has been done. And I will give in the notes some reference where all this is actually worked out in some detail. But I mean, in order to get somewhere, I will just focus on a simple example, which is just single quark density matrix. And then the density n of x is just delta of x minus r operator, which means that in order, I mean, actually, this is partly answering your question. This operator here, n of x into r prime, it's a delta of r minus r prime, delta of x minus r, right? So this here is an operator and takes a matrix element. This is diagonal, and it's a delta function. So now let's see what this operator, so let me take the matrix element of L1d r prime. Okay, this is the first operator, which is here, and I take the matrix elements r prime. So you see, if I do that, you see, I have, well, let me do it. Sorry. So this is minus I. Do I have it? Yes, I have it here. Minus I over 2, the integral of x prime, v of x minus x prime. And then I have r and x prime, commutator with d r prime. Okay? But you see, this commutator here vanishes because this is local. So this is n of r, matrix elements r d r prime. And the commutator will not change the result. So this is 0. It tells you simply that the single quark does not interact with itself by Coulomb interaction, right? So now let's see L2. So L2 turns out to be W0 minus W of R minus R prime times R d R prime. And this is what I call this difference here of W. This is what I call minus gamma R minus R prime times R d R prime. Okay? And you see now a very interesting effect of this W, because you see the density matrix here, when it is non-diagonal, will be damped by gamma. So if I look at the evolution due to this L2 operator, what I will find is that after some time, the density matrix will become diagonal in coordinate space. Okay, and that has to do with there is a damping of the non-diagonal matrix elements. It's related to this phenomenon, the phi function that I mentioned before, and this particular damping goes under the name of decoherence. And from what we have seen a moment ago, what is really responsible for decoherence here is the collisional processes. So it's collisional decoherence, which means that because of that phenomenon, the density matrix becomes more and more diagonal and eventually becomes a classical object, which is just a density of heavy quark. You observe, by the way, that when R is equal to R prime, there is no decoherence, which is okay because the density remains constant. It cannot be damped by collisions. Okay? And now what is L3? L3 is 1 over 4 times mt. Then there is a whole bunch of terms, which I may write in full or not. Let me put ... Essentially, these are terms which involve the second derivative of this W. And I will show in a moment that these are the typical ingredient which determine the transport coefficient. Okay? So let me try to do that. then I show the results. So I need to do a couple of steps here. You see that because of this phenomenon of damping of the non-diagonal matrix elements, after some times, the density matrix, which I call D of R and R prime, not to write all the, I mean, inside rather than the bracket notation, I'm going to write this as a function of capital R and a variable y. So I call R is R plus R prime over 2, and y is R minus R prime. And what we expect is that as time progresses, the y variable becomes smaller and smaller. So under this condition, L0 becomes simply I over m times gradient R gradient y. L1, as we saw, is 0. L2 becomes simply minus gamma of y. And L3 becomes 1 over 4 times mt times Laplacian of w of 0, which means the Laplacian of w of x at x equal to 0, minus wy minus 2 gradient y, w of y, gradient y. So it's an operator which acts on this function here. Okay? So this is still exact. I mean, what I've done is taken this equation, do the substitution which are appropriate for one particle density matrix, and then substitute the coordinates as indicated here. So there is no further approximation done. But now I will do the semi-classical approximation. And we have been discussing various aspects of this approximation. In the particular context, this approximation amounts to exploit the fact that the density matrix is nearly diagonal. So this is an expansion which I'm going to do in powers of y. If I do that, then let me skip the detail. And so expand in small y, and then take a Wigner transform. Which means that I rewrite d of r and y. I define a function d of r and p, which is the integral over y, d3y, exponential minus ipy d of r and y. So the Wigner transform is just to replace this small variable y by the conjugate momentum p. And then if you do that, this whole equation boils down to the following equation, d by dt plus v dot gradient r acting on d of r and p is equal to 1/2 eta gradient p squared d plus gamma gradient p of v dot d, v dot vd, sorry, where v is equal to p over m. And this is a Fokker-Planck equation, okay? So this is a Fokker-Planck equation for the motion, for the evolution of the density matrix of the heavy quark. And from the Fokker-Planck equation, you can, of course, immediately write the corresponding Langevin equation, in terms of which you can solve the Fokker-Planck, which is gamma times r dot plus psi of t, where psi of t prime is equal to eta times delta of t minus t prime. And this parameter gamma and eta are not arbitrary parameters, but they are, of course, related to the W.
So a question. So
Yeah.
when you do the semi-classical approximation,
I'm sorry?
when you do the semi-classical approximation, do you replace the quantum fluctuations of the gluon? Like semi-classical means one of the quantum degrees of freedom you have frozen the quantum fluctuations. So when you get this effective fluid motion kind of thing, which quantum degree of freedom you have actually suppressed?
I don't know how to answer that question. You see, the W is an object which incorporates precisely those quantum fluctuation. Remember, it's coming from the spectral function of
the algebra is clear to me. I was just trying to interpret in terms of physics that when you have a full quantum system to a semi-classical system, that means some quantum degrees of
well, yeah, but it's not trivial to see what happens to the original quantum fluctuation, because they are incorporated there in the W. But what I have been doing here is just exploiting the fact that, of course, we know a priori that the quarks are almost classical objects for various reasons that I have commented before. But in this particular framework, the semi-classical approximation is coming from the fact that the density matrix in the coordinate space representation is becoming diagonal. And I will show you now. I can switch to slides here for the last 15 minutes.
Off-diagonal terms capture the quantum correlations which you are suppressing.
The off-diagonal, the fact that the density matrix of a single heavy quark is non-diagonal is genuine quantum mechanics. Okay, it includes the phases of the wave function and its complex conjugate, right? Now, so that. This is the part which we treat as a semi-classical approximation, right? And the rest is hidden in this function here. So what I've not done, but let me ask you to trust me, is that eta and gamma are are fixed by W, from W. Okay, so once you know W, you know how to calculate the drag and the noise term without any ambiguities, and there is no issue about the fluctuation dissipation theorem because this is built in the microscopic description. So now yeah. Yes, I need to switch to the slides, so somebody should help me with the computer. I would like to show you a few results of all this machinery. But please, your question. I mean, yeah.
What I have still understood is that A0 is not fluctuating quantum mechanics. A0 is not having any quantum fluctuation.
I have difficulty to hear you.
So what I have understood is that A0 is not quantum mechanically fluctuating.
What is not?
Oh, sorry, it has no quantum fluctuation. A0 doesn't have any quantum fluctuation.
What do you mean by quantum fluctuation?
Quantum fluctuation means there is a mean and then there is another quantity which is oscillatory. It has no such component. That's what I believe.
Well, I don't know exactly how to answer that question. The approximation is called semi-classical, which means that we keep tracks, nevertheless, a little bit of quantum mechanics. But these are limited to a very small region of the phase space for the variable. Let's put it that way.
Thing which is fluctuating is some other mode, I believe. What you showed in the calculation, it is not A0 that is directly fluctuating. So some mixture of W0.
The A0 fluctuation are properly taken into account when I calculate the W.
Yeah, but that is not.
So the W determines that the W contains all the quantum fluctuation of the field of the gauge field.
Yeah.
Okay. Now, when I calculate the motion of the heavy quark, all this information about the quantum fluctuation is incorporated in an object that I call W. And what I've done here is that I've gone one step further. I say, okay, since the motion of the heavy quark is nearly classical, I can use this semi-classical approximation and then derive equation which exploits this approximation. And this equation turned out to be simple transport equation for which all the parameters are completely determined by the W. So the transport coefficient which enters this Fokker-Planck or Langevin equation are determined by those quantum fluctuations that you are referring to.
Yeah, so the fluctuation modes are not directly the A0. It is some combination of the quantities which are encoded by W and some function type of thing, I believe.
The fluctuation of A0 do not show up explicitly in the final equation. This is what, if this is what you want to say, this is correct. Okay, but they are there. They are hidden in the value of the transport coefficient. Yeah. Yes, exactly. You have to, you make an expansion in Y to second order in Y, and the Hessian matrix, I mean the second derivative matrix of the W with respect to Y carries information about the transport. And they are obviously related because it's the same object. Okay. So maybe now, I mean, just to relax a little bit and show you that this whole machinery eventually can be used to produce results. I should be able to use that apparently. So these are some illustrations that are based on two papers, which I guess I quoted already in the colloquium last week. These two papers they're on archive and they are published, in fact. So as I was, well, I don't have time I did not have time to argue very much about QCD, but realizing the program that led to the simulation that I showed yesterday in the context of QCD turned out to be much more difficult than I anticipated. And this has given birth to all this heavy machinery that I have presented today and yesterday. But in order to try to progress and understand this, the structure of this equation, we found it useful to go to a artificial world, I mean artificial in the context of QCD, of one dimension. By suppressing number of dimension, we make the problem easier to solve both numerically and analytically. I mean, in one dimension, particle just go on straight lines, and that makes easier. So my colleagues in Nantes, Paul Bernard Gossiot and collaborators have cranked a potential in 1D, which somehow mimics the physics of 3D heavy quark. So this is the typical potential that is going to be used in the result that I show. This is a real part of the potential. So there is obvious, well, there is a screening at short distances, and the force between the heavy quark disappears at long distances depending on the temperature. So the various curves here represent the temperature in GeV. So this is 180 GeV, 180 MeV, 200 MeV, etc. And this is a potential, the imaginary part of the potential. It has similar features and the quadratic behavior, singular quadratic behavior near the origin. Okay, so this is now I refer in the talk and in the seminar last week about different regime in open quantum systems.
Can you show that imaginary potential again?
Yeah.
Yeah. So
this
somehow
is this is 130 MeV. Yeah. Okay.
At 130 MeV. Somehow the
I don't think we use 130 MeV because for the reasons which I will explain.
No, but just for the form of the potential, I do not. I mean, somehow it looks like that imaginary part becomes very large at large x.
Yes,
low temperature.
I don't think this is very physical, but I don't know why they put this curve. I mean, it's not, we are not going to use this before 150 or 200 MeV. Okay, I'm not responsible for that. I'm just, go to that paper where you will find the whole details of, I mean, there is a lot of yeah, cooking there, which I don't remember the details. But anyway, there is a real part and there is an imaginary part, and this is what I want to exploit. So this is a typical result that characterize the regimes which we want to explore. So this is for one QQ bar pair, either a CC bar or a BB bar, with numbers which are, as I said, the potential characteristics and parameters are chosen so that the numbers which come out are representative of what you expect, I mean, semi-quantitatively for either CC bar or BB bar. So this is the binding energy of a CC bar pair. I mean, forget about the beginning here, but it's the same thing as for the imaginary part. The physics below 180 MeV is probably not very precise. But the binding energy, of course, decreases as a function of temperature. And there are two other characteristic quantity, which is the double mass and the width, the decay width of the J psi. And depending on when you cross the binding energy with the double mass or the J psi, you have a different temperature which characterize the regime of open quantum system you are in. So most of the discussion that has been, that I have presented in these lectures are valid above this temperature, TQBM, which is in this region here, where I assume that the double mass is larger than the binding energy. Now, in this, in the BB bar, the situation is a little bit different because much of the physics is actually in this range of temperature for which this approximation I've been developing is no longer reliable, and we should choose a different basis. So let me stick to the CC bar. This was just to mention, to emphasize that there are different regimes of open quantum systems, and depending on the regime you are in fact, the choice of the basis in which you analyze a problem is different. In this regime of a quantum Brownian motion, the coordinate space basis is the most useful because the density matrix becomes diagonal in that basis. In the so-called optical regime, the bound states, the fact that you have bound states with different quantum numbers is the appropriate description because you can think of transition between these bound states with little modification of their intrinsic properties and stuff. Okay, so how do I move forward? Oh yes, this is, so now I want to illustrate a little bit the semi-classical approximation by showing you a few tests, a detailed test of this approximation in the abelian context. Okay, so this is not yet a QCD quite, but let me now look at the density matrix. So it's the density matrix of a QQ bar pair. So now I have two coordinates, x1 and x2 in the bra, x1 prime, x2 prime in the ket, which I call, which I write this way, and then I do what I just did a minute ago. I'm going to shift to relative coordinates. So there will be an S on the left, x1 minus x2, and S prime on the right, x1 prime minus x2 prime. And I call this object ds S prime. And this is the plots which are here with S prime on the vertical axis and S on the horizontal axis. So you see, I start at initial time by a singlet initial state. Okay, and this is perfectly spherical in this representation. And after a time of order 5 Fermi, you see that something develops along the diagonal, and you see these decoherence processes coming in. The density matrix become more and more diagonal. You see there is a little spot red here. The red, the color is the color code is increasing density from blue to red. There is still a bound state here remaining at time 20 Fermi. But the major thing which I want you to remember is that the density matrix does indeed evolve to a diagonal matrix. Now, let me let me go into more detail. So I take an initial wave packet, which is just a Gaussian like this, and then this is the evolution at a temperature of 300 MeV. And the beginning of the evolution, you see, is rather complex. Again, the color code from blue to red represents the increasing density. And obviously, this is now in RP space. So this is the coordinate, the relative coordinate, and the momentum. And this is the exact solution of the equation which were on the board, not the transport equation. And on the right-hand side here, this is the semi-classical evolution. So you see the semi-classical evolution at early time, at the time 1 Fermi over C, already washes out all these quantum interference which are responsible for this fine structure here. Forget about the middle column. So here you see that at 10 Fermi, you see that the evolution with the exact equation and the semi-classical is really good. And at 20 Fermi, you can hardly see any difference between the two evolutions. Now, we can make that more quantitative by doing, I mean, there is a lot of mathematical studies on this kind of problem. And we can introduce an abstract object, which is a distance between the two solutions. One is the exact quantum mechanical solution, and one is a semi-classical evolution. I mean, it's a Wigner transform, as I said before. So it takes the norm of this difference, integrate over the phase space, and you plot that as a function of time. Now, if the two objects are the same, the distance should be 0. If they differ, the distance is positive. I mean, you can show that it is positive. But it is a norm, so it is by definition positive. So if you look at the beginning of the evolution here, this is at small time. Since you start with the same initial condition, of course, the distance is 0. Then there is a very rapid increase of the distance because of the initial quantum mechanical interference effect. And then the evolution, irrespective of the temperature, almost flattens and remains essentially independent of time. So this is a measure of the accuracy of the semi-classical description, which is a rather stringent measure because you're looking now point by point to the difference between the quantum mechanical solution and the semi-classical approximation to it. And now the last plot is one of the most important.
From that figure, what are the informations that you are saying are like concrete? I mean, I guess the actual value of D is probably, I mean, it's not monotonic in temperature. So I guess.
Well, yes, we can discuss. Let me skip that discussion because I still have more slides. And if you're interested, there are a whole paper where we have explored several distances, and there is indeed some information in the temperature dependence here, which requires a more detailed discussion. But the important point, I mean, the most important point, which I want to make is the following. This is the impact of the you see that all this evolution contains a Hamiltonian evolution, that is to say, a unitary evolution. Start from a state, you go to another one by unitary evolution. But there is non-unitary processes. There are collisions in the system. And what you see here is at the same distance, which I was mentioning before, if you forget about the non-unitary processes, you get the blue line here. And you see oscillation, which are somehow characteristic of underlying quantum mechanical process. Now, if you switch on the non-unitary dynamics, this is this red curve here. You see the initial state, I mean, evolution of the distance is the same, but basically after a very short time, you get, I mean, the reason why it stays constant and not decay to zero is something we can discuss afterwards. But the main point is that there is a dramatic reduction of the distance, which means that the semi-classical, the collision in the system via the non-unitary processes makes a semi-classical approximation much more reliable than you would get in the absence of these processes. So now let me switch on to QCD. There is not much to say which is not already included in QED. This is the same type of evolution for now. Density is a singlet density matrix or the octet density matrix. So this is again SS prime in the coordinates I described before. So you start with a symmetric state. You see, as a function of time, you see the development of this diagonal structure, whether it's octet or singlet. It's the same physical phenomenon. And again, this is a slide I showed last week. This is a density now, the diagonal part of the density for singlet or octet. So you see that the evolution, this is exact now, a quantum mechanical evolution. The evolution has the tendency to equilibrate the color. You see, we start here with a color octet and color singlet, which are completely indistinguishable. And as the time passes, you see the dotted line represents the octet, the full line represents the singlet. So the singlet decays slowly, but the octet contribution is almost vanishing. And at late time, what you see is that there is a little remnant of a bound state here in the singlet channel, and the octet is completely flat or slightly depleted. This flat density here represents the average density in a box of 10 Fermi, or twice 10 Fermi, which is a box in which the simulation is being done. So there is, I mean, the equation do what you expect, namely in a finite box, you equilibrate the color between the various components of the density matrix. And finally, I would like to emphasize one issue which is not completely resolved even in a more general context of the Lindblad equation. This is a question I was asking Akamatsu yesterday. And this is interesting physics, which is not completely understood. I mean, we understand numerically what is going on, but the physics is still a little bit unclear. This is a comparison of the asymptotic states with a QED. I mean, I'm doing now what I call QED is QCD without any with all colors being equal. So it's this is factor NC squared here indicates that what we're doing. So the temperature is 200 MeV or 300 MeV, and what's plotted here is a probability Pn to find the system in one eigenstate of the full in medium Hamiltonian after a long time. So this is the asymptotic solution of this equation here. This equation of d by dt times some operator acting on d. So if I set d by dt equal to 0, then I have a solution, and naively, one expects the solution to be the Boltzmann distribution. So the dotted line represents the Boltzmann distribution. There is a correction factor here, which we understand, which we can calculate, which reflects the fact that quite generally, these Lindblad type equation do not converge to the Boltzmann distribution. But you see, if you forget about this correction factor, basically we have a beautiful exponential law, forget about the large energy here, and the color points here represent the bound states in the system. And these are continuum states which are discretized in the box. So for QED, you see, you have a complete, I mean, you think you have a complete understanding of the situation. It goes, the semi-classical approximation takes a system where you expect it to go, namely to a Boltzmann distribution, to within this little correction factor. And the same, of course, occurs at 300 MeV. At 300 MeV, you have less bound states. Some of the bound states have disappeared, one remains, but you see it's perfectly well described by Boltzmann. Now for QCD, the things are completely different. This is still the dash line, the black dash line represents the Boltzmann limit. It's the same type of correction factor included, but you see that the bound states do not obey at all the Boltzmann statistics. At higher temperature, only one bound state remain, and it's not too far from the Boltzmann limit. So what's going on here is something we can partly understand by looking at the eigenstate of the Hamiltonian. And this is a plot of the first few eigenstates as a function of temperature. So this is the eigenstate of the Hamiltonian. So you have the 1s state. The 1s state is not too different between QED and QCD, okay? But you see that the 2s state is almost the same for H and D, QED, but the 2s is completely delocalized in QCD. So if the eigenstate of H are the same as the eigenstate of D, then you can argue that D commutes with H, and the eigenstate of the Hamiltonian are the good representation for the density matrix. For QED, this is perfect, and in the stationary state or the long time limit is completely seems completely under control. You see, for DS, for the density, for the singlet part of the density matrix, this is not the case. 2s states and the 1p states are completely different from the 1s, from the 2s and the 1p states of the Hamiltonian. So is this due to the fact that somehow the 1p states are actually for DS, I mean, are coupled to the octet, which are not bound, and therefore they occupy the whole of the box? That's something which we don't fully understand. I mean, we have hand-waving arguments to explain this, but this is interesting physics which remains to be explored. So with this, I guess I am done for today. So thank you.
If you increase the box length, does the 2s state die down?
If we increase the box, oh, this is
For the third column, like
I think we try to increase the box, and it doesn't change much the picture. You see, well, you see that the difficulty is really localized in the first few bound states. You see, this blue curve here is a tense bound state. I mean, by bounds, it's a state in the continuum, but in the box. So this is a discrete state. Okay, and you see they are not too different. So the density matrix for the continuum states is almost diagonal in the basis of the Hamiltonian. And this is what actually is reflected in the fact that you don't see deviation from the thermal distribution for the continuum state.
yeah, so that's why I was wondering if the deviation is coming from the box length for the bound state. So
no, I don't think this is a box. This is not an effect of the box size, because you see for QED, you can apply your argument for QED. There is absolutely no effect.
yeah, because for the QED, the state dies much before. I mean, the value of the wave function is very small at the end of the box, right?
No, but everything is done in a box of fixed size. Okay, so we calculate the eigenstate of H. The question is whether the eigenstate of H or the eigenstate of D. That's the question. Okay, irrespective of the size of the box.
Yeah, but the box matters, right? Because
it does. It does if you are interested in the precise value of the energies. It does, because the states are quantized by numbers which depend on the size of the box. But the size of the box is not really relevant here. And I don't have the slides here, but if you go to the paper, you will find, I mean, we have done checks to analyze as a function of size. It doesn't matter. Doesn't matter.
Yeah.
It's not a finite size effect.
Just a comment regarding your question. So if you discretize the box from the, I mean, if you limit the box size from infinite size to a few Fermi, and if you put the box size R is almost is equal to lambda, h by momentum from the uncertainty principle, then you can calculate that the momentum integration value doesn't change much in that Fermi, the S is equal to 10 Fermi, 7 Fermi range. So that you can check.
Yeah, yeah.
Just saying it because by definition, the wave function of the bound state should, go down, right? But for 2s, it's not going down.
But it contains integration over the momentum.
I'm sorry. Go ahead. Go ahead.
It's integration, some integration. So if you integrate and calculate, the numerical value doesn't change much.
Maybe we can have this detailed discussion in lunch. So before we leave, we want to thank Professor Blaizot again for this excellent set of lectures. And thanks for coming. And we break for lunch and reconvene at 3.